then you can solve the what? Then you can use the equation where we started from left to right, because you need to know what is going on at point A. Okay, so it's a longer method. So I find this method, it took me quite a while to get used to it. I'll tell you that. And the reason why the integration part is easy. Okay. The thing is, you have to trust the math. Okay, trusting the math is not something that we can achieve like overnight. Okay, Eugene say trust the math. Okay, let's trust the math then. Okay, so it takes a while to get used to it. Okay, so what you see down here, what I want to drive is this: distributed load equation is still the same. Now the holding is different, the boundary condition change. Okay, so that's what we learned down here. You can see down here, when v equal to 0, m is equal to 0, when x is over here, we only know that when the configuration change, so both sides now is one pin and one is roller, the boundary condition changes. Okay, but the math is still the same. The distributed load equation is still the same. Okay, very interesting. Sorry, I find interesting. Okay, right. So that's what we mean by integration method. So I'm going to put on extra video to show you how to handle how to use this technique when you also have a point load. Okay, if the end of the class I have time, I'll show you. Okay, so now the next technique that the next topic I'm going to teach. Okay, next topic I'm going to teach. I'm just going to do briefly. We go for a break at 10:30. Okay, so the next technique that we're going to teach is known as the Elastical Method. So deflection, of beams using the elastic okay, we're going to use the elastic curve method. So the elastic curve,
Eugene,
yes,
sorry for the previous section. Are we also gonna have to learn how to do the integration method for curves?
yeah, that's what we're doing now.
Okay.
Okay, so the elastic curve method, okay, is used to calculate the slope and deflection of the beam. Okay, that's what we call elastic curve. So the elastic curve technique has one equation. I'm not going to derive this equation. I want you to apply this equation. Okay, deriving this equation will take me half an hour, and I find it pointless. So E over E multiplied by I is equal to the d squared y over dx squared, and this is equal to the moment as a function of x. Again, what is observed over here is you do see what? You do observe moment as the function of x again. Okay, you do observe the moment as a function of x. Okay, so from here, so this equation over here is what we call the elastic curve method. Okay, this is what we call elastic curve method, where E is the Young's modulus, I is the second moment of area, right? M, so this is the moment as a function of x. Okay. So if I'm going, we're going to draw. I'm going to draw a beam now. Okay. So we're going to draw a beam. Okay. I'm going to sketch a beam. And the beam, for this case, we are going to look at a beam that is simply supported. Okay. So the beam is simply supported. It can be any configuration, but for this case, we are going to take it as the beam is simply supported. Okay. Then we're going to have axis. So this is your x. Okay. And then your vertical. This is going to be your y. Okay. Now we're going to put a load on this structure. Okay. So the load is the structure is loaded over here. The load over here is P, right? So when the structure is loaded, the next one I'm going to draw is I'm going to draw the deflection. Okay, I'm going to draw the deflection. So again, we have our axis. So this is our x, right? And I'm going to focus on the negative, the minus. Why I'm going to focus on the minus is because the deflection will go into the negative, right? Then we're going to have our y. Okay, so what I'm going to sketch now is the deflection of the beam. Okay, so the deflection, so it's going to come down here, right? So this is the deflection of the beam. Okay, so there's the deflection of the beam down here. So now, if we want to find, what we're trying to achieve is this. If we want to find the deflection, right? So now I want to find this. Okay, what do I want to find? I want to identify at a certain distance x. Okay, at a certain distance x, right? At this point now, okay, I want to know, or we want to know at that point, right, what is our y value? Okay, so at this point, right, what is our y value? So this technique enable us to know at every single point what is the distribution. Okay, and then if we come to a slope, somebody say, what is a slope then? Okay, so if you look at, if I'm going to draw a line, the green line, okay, it's going to touch the tangent of the curve. Okay, so this is touching the tangent of the curve, right? Anti-clockwise from here, that is the slope. Okay, so this diagram is how the deformation pattern will look like by obeying the elastic curve equation. Okay, so by obeying this elastic curve equation, we have to know this configuration. Configuration in what sense? Okay, we want to know x distance, knowing that the datum start from 0 will always be on the left hand side. Okay, and then we can determine the slope theta, and also we can determine the deflection y. Okay, so now how about do we go in doing this? And this is not any more complicated at all. Okay, so I'll write for you the solution procedure. Okay, I'll write for, so the solution procedure, right? The solution procedure is as follows. Okay, so again, we go back to this. dv by dx is equal to, so we have dv. Oh, it's near the end of page. I will start on a new page. Okay, so the solution, or let me see if I have more space. Yeah, I have more space on the side. So I will do this. Okay, I will bring this up. Okay, then I'll draw a line. Okay, so I'm going to write out the solution procedure. Okay, so solution procedure. Okay, so we're going to have solution procedure. So we're going to have dv by dx is equal to minus omega as a function of x. So we still need to find the what? The equation of the distributed load. Okay, we still need this, right? We still need to identify the equation of the distributed. Then after that, we're going to integrate, right? So from here, we're going to integrate one time. Right? So when we integrate, we have v as a function of x, right? We integrate minus omega as a function of x dx, and then we have c1, right? And this, we know this is also equal to dm by dx. Then from here, what do we do next? We integrate again. We need to integrate the second time for the fact. Okay, why do we need to integrate the second time? Because we need to apply the elastic curve equation, which I'm highlighting in yellow now. And the elastic curve equation is related to the moment equation. Okay, so now we use the moment equation again. So after we integrate the second time, once, twice, now we will have c1x plus by c2. Okay, then after that, we're going to apply. Okay, from here, we're going to apply the elastic curve equation. So what do I mean by elastic curve equation? It is just this: EI d squared y over dx squared is equal to m as a function of x, and is equal to minus omega as a function of x dx once dx twice plus by c1x plus by c2. The next thing we do, okay, you guys will say, yeah, Eugene, we're going to integrate that what? The third time. Okay, we're going to integrate the third time. So when you integrate the third time, you have EI dy by dx. Okay, so this will be equal to EI. So dy by dx is EI theta. And that's the equation of the slope now. Okay, then this will be equal to 3 times 1, 2, 3 minus omega x 1, 2, 3 plus by c1x squared over 2 plus by c2x plus by c3. Okay, and finally, before we go into a break, we integrate the fourth time, right? So this is equal to e I y. So this will be equal to 1, 2, 3, 4 minus omega as a function of x 1, 2, 3, 4 plus by c1x cubed over 6 plus
Can
by.
you scroll down, please?
Oh, sorry. Sorry. Yeah, I'm writing. I do apologize. Right? So c2x squared over 2 plus by c3x plus by c4. Okay. So it's just matter of what? Integrating. It's just matter of integrating. Okay. So what I propose now, I will ask you all to go for a break. Okay. Then we come back at 10:45. Okay. We go for 15 minutes break. We come back at 10:45. We continue.
So the deflection is the EIY?
Yep.
Okay.